3 pi, 4 by 3 pi. Okay, so x cube ZE by r cube, nothing, right? So that is the charge enclosed in this sphere. Okay, very good, sir. You calculated the charge enclosed in this sphere. Okay, at this instant, there will be two forces acting. One, Lorentz force due to the applied field. Now, this applied electric field has actually created this suppression, right? So, E into ZE, E into ZE, okay, will be the force acting on negative charges as well as the positive charges. Okay, now when these two charges got separated, charges got separated, Coulomb force comes into picture. Okay, Coulomb force comes into picture. Now what is the Coulomb force? Q1 Q2 by 4 pi epsilon naught r square. Q1 Q2 by 4 pi epsilon naught r square. What is Q1? Okay, positive charge that is inside the nucleus, that is ZE, and negative charge. What negative charge? I have to take the negative charge which is enclosed in this sphere. Okay, so the amount of negative charge that is enclosed in this sphere is Q dash. Okay, ZE plus into Q dash minus by 4 pi epsilon naught r square or x square, because x is the separation between these two. Okay, now this is the Coulomb force. Clear? So in this particular situation, after applying the electric field, okay, here you don't have any new, okay, net, okay, force. But after applying the electric field, okay, we have two forces. One is Lorentz force because of the electric field, that is ZE into E. And another is Coulomb force, that is Q1 Q2 by 4 pi epsilon naught r square. Okay, here Q2 is nothing but Q dash and r is nothing but your x. This way I have two forces. Okay. Now, will the separation go on? Will the separation go on? No, no. Okay, they stop. When do they stop? When they reach equilibrium. Okay, when do they stop? When they reach equilibrium. So when they reach equilibrium, okay, Lorentz force is equal to the Coulomb force. Lorentz force is equal to the Coulomb force. That implies ZE into capital E is the Lorentz force is equal to the Coulomb force. Coulomb force is nothing but ZE plus Q dash minus by 4 pi epsilon naught x square, whereas Q dash already you have calculated as x cube ZE by r cube. I substitute here. Okay, when I substitute here, I have E is equal to this expression. E is equal to this expression. Okay, now, okay, this is not A. Sorry, ma. This is not A. This is alpha. Okay, whatever you see here is basically alpha. I think symbol got changed. Okay, right. This is not A, alpha. What did we define alpha? Polarisability. Dipole moment produced per unit electric field. Dipole moment produced per unit electric field. Clear? Now, do you know the expression for electric field? Yes. Do you know the dipole moment? Do you know the dipole moment? I'll give you 10 seconds. I want you to answer. 10, 9, 8.
Displacement into
Charge into
charge.
separation.
Yeah, good. Answer is excellent. Charge into separation. Okay. What is the separation between the two charges here? 5, 4, x. Excellent. What is the charge? Yama? X is the separation between the two charges, right? What is the amount of charge that we have to consider? 5, 4, 3, 2,
ZD.
1. Beautiful. Beautiful. Okay. ZD is the charge because this is the negative charge center and this is the positive charge center. What is the value here? Minus ZD. And what is the value here? Plus ZD. Okay, so negative charge center and positive charge center are separated by distance x, and their values of charges are Z into E, where Z is the atomic number and E is the charge of okay, elementary charge, that is a charge of the electron or charge of the proton. Okay, so you know mu value, that is Z into small e. You know capital E, that is okay, this expression. So please find out the electronic polarizability, alpha electronic, that is electronic polarizability. Okay, that's only substitution. Okay, okay, I'm not going to do that. Okay, you're going to get the expression for electronic polarizability. Okay, right? Okay, once again, without the electric field, okay, the negative charge center and the positive charge center are at the same point, and electrons are distributed throughout the volume of radius r. So the volume density of the charges, negative charges, is ZE, the total charge, electric charge, divided by volume, that is 4 by 3 pi r cube. That is the charge density. When electric field is applied, the negative charge center and the positive charge center get separated. Okay, and the separation, let me consider as X. Because of this separation, okay, there will be some charge within this particular circular surface, sorry, spherical surface, spherical surface, which will be attracting the positive charge. That is Coulomb force comes into picture. Okay, Lorentz force, that is force because of the field, is ZE into E. And the Coulomb force over here is ZE Q1, okay, that is Q1 Q2 by 4 pi epsilon naught x square, where Q1 is ZE and Q2 is Q dash. Q dash is the charge enclosed in this sphere. What is the charge enclosed in this sphere? Okay, the volume of the sphere is 4 by 3 pi x cube, and the charge density as you calculated here is ZE 4 pi, okay, ZE by 4 by 3 pi r cube. I substitute both of them and I get Q dash is equal to x cube ZE by r cube. Good. After the separation, you have Coulomb force, and before separation and after separation also you got Lorentz force. So under equilibrium, Lorentz force and Coulomb force will be equal. Okay. So Lorentz force is ZE into E and Coulomb force is this expression. I equate these two things and try to get the expression for electronic polarizability, where electronic polarizability or polarizability is nothing but dipole moment produced per applied electric field. This is the applied electric field there. Okay, and I want you to calculate mu. Okay, what is mu? ZE into E, ZE into E. Okay, so you know this and you know the applied electric field. Substitute both of them. Okay, I think this is also somewhere different. Okay, yeah. See, what's happening is I prepare this in one system, and after that, it's when I change to another system, it's getting disturbed. Okay. Okay, is equal to right. Okay. So ఇదేంటి ఇక్కడ ZE. Okay, this is the expression. Okay, anyway, from this expression you calculate okay, what is electronic polarizability? What is electronic polarizability? Okay, ఇక్కడ ఏమైనా సింబల్ మారిందేమో I'm unable to see. Okay, this is the expression and you take ZE to the other side. Okay, yeah. So out of these two ZEs, one ZE get cancelled and this is the expression that you got. Okay, mu E by R cube. Okay, whatever it is. Okay, so you please tell me what is your electronic polarizability? What is your electronic polarizability alpha? Okay, you know the expression for E here and I want your alpha. Okay, am I clear? Right. Okay, you got 20 seconds to read this slide. Oh, sorry. Okay. I actually prepared a small animation here, but it's not working. Sorry, చూద్దాం.